Hello. So, we have at last come to the end of this course on computer architecture and organization. So, over the last 12 weeks we have discussed the various features and concepts that are pertaining to computer organization and architecture. We have looked at some of the basic concepts. We have also looked at some of the advanced concepts that are there in many of the modern day processors. So, before we say goodbye to you, we would like to summarize the coverage of this course as we have carried out over the different weeks. So, I would be requesting Dr. Datta to talk about the first 6 weeks of the course which she had handled.
Okay. So, we have covered 12 weeks in total. Initially, we started with the evolution of computer system, where we have looked into how computers have evolved over the years, and of course, where we stand today. In fact, the last lecture which you have heard, that would have given you a picture of where we are now. We have also discussed about the basic operation of a computer, how a particular instruction is executed, what are the operations a computer performs, various memory addressing and system softwares. Like when we say that we are executing an instruction, we have shown that we store the instructions or the programs, you can say, in memory, and one by one we bring those instructions through some registers to our processor, and then we execute it. In this process, we require two important registers, that is memory address register and memory buffer register or memory data register. Then we talked about various software and architectural types like von Neumann architecture and Hardwired architecture. If you recall our discussion of von Neumann architecture, there we discussed about that how both program and data are stored alongside, and each time processor needs to access a particular data or instruction, it fetches from memory, bring it to the processor, and then it executes. But both, if you want to access either the instruction or the data, you have to hit to the same memory, because we are storing both the data and the program in a same memory. So, this kind of architecture is called von Neumann architecture. And we also discussed about Hardwired architecture, and we have seen that in Hardwired architecture we store the data and instruction in two separate memory, and this is widely used when we have discussed cache memory. So, we have seen the advantages of using both Hardwired architecture as well as von Neumann architecture. And if you think of that, going from the first lecture to the last lecture, some way or the other you can relate these two methodologies or these two basic types of architecture that we have discussed. We then discussed about instruction set architecture. Basically, ISA is the programmer view of the computer, how the programmer actually looks, sees the computer. I mean, what is happening inside the computer. Like when we say a programming model, through that programming model, we can actually bring out how we can execute an instruction. Step by step, what are steps required, we can actually have it in more detail if we looked into the programming model. So, ISA is the programmer view of the computer. Then we moved on with week 2, where we have briefly discussed about number representation, and then we moved on with number representation in later part of the later weeks of computer arithmetic. We discussed here a very important aspect of instruction format and addressing modes. So, what do you mean by instruction format? An instruction consists of two parts. I have discussed it in very much detail. that add A comma B. So add is the operand and A comma B is the add is the opcode and A comma B is the operand. So an instruction is divided into basically two parts, opcode and operand, and we have seen specifically for MIPS architecture we have discussed that how the instruction format is. Then you think of that how the computer will understand that okay, this particular data that is in the operand will be fetched from either memory or from register. So various addressing modes that are used today and that are existing, we also discussed about that, and we closely discussed about CISC and RISC architecture, and as a case study we have taken MIPS32 instruction set, and we have discussed the various programming. Then we also discussed about SPIM, which is a MIPS32 simulator. So we have shown small code snippets where we have written some assembly language code for some very easy program, adding two numbers or factorial of a number or a palindrome of a number. Those examples we have shown, and through those examples what we have seen is that that how we can write an assembly language code and how an assembly language code using SPIM can be executed. So we have seen that. Then we moved on with week 3, where we actually discussed about the quantitative approaches in evaluating the design alternatives. So by this what we mean is that this is a very important concept in modern day technology if you think of it, and here we actually shown that how we can say that a computer A is better than computer B. On what ground you can say that? What are the how quantitatively you have to say that? We just cannot say that okay, this computer is better than that. So what are the design principles that are followed? So we discussed about that. Then we have taken many examples to evaluate it, and the famous Amadani's law and its applications we have discussed. Then we moved on to week 4, where we discussed about the design of control unit, how the instructions get executed inside a processor, the concept of micro instructions and microprograms, and then we also looked into two different ways, namely hardwired and microprogrammed control unit design. So in hardwired control unit design, we have seen that it is much faster and how the instructions that needs to be executed must be simpler in nature. And microprogrammed control unit design, where complex instruction can be executed in some way or the other. We have a processor inside a processor, so we have a similar kind of mechanism like processor does. It fetches some data from memory, it executes it. In the similar way, microprogrammed control unit, it fetches some codes, some micro instructions from the small memory, and then it executes it one by one. And here we have also discussed the non-pipelined implementation of MIPS32 instruction set architecture. Then we moved on with week 5, where we discussed about, we have been discussing about processor memory interaction from the beginning of the lecture if you remember, but we actually moved into what is memory in week 5, where we discussed about the various memory technologies that are used today, and what are the types of memory that are there. We discussed thoroughly about the memory interfacing. We cannot use a very large memory, how a smaller memories are combined together to form a large memory. Memory modules are combined together to form a large memory. We discussed about all these aspects, memory interleaving. So all these things we discussed in week 5. Then we moved on with week 6, where we discussed about memory hierarchy design. So when we call a memory hierarchy design, that means how we are moving from one level of the memory to the next level, to the next level, and so on. So if you think of a processor, inside processor you have some registers. Register is ultimately some kind of memory only. It is storing some kind of data. Whatever is storing some kind of information, data, it is a storage unit. Then you move down to the next level where we have seen cache memory. So that is the next level of memory where you have cache. So cache is a kind of memory which sits between your processor and the next level of memory, that is main memory. And what it does, frequently accessed instructions or data are brought from main memory to cache memory, and then it is sent to the processor. The next level after main memory is other disk and other memory systems that are there. So this is how the memory hierarchy is existing. And one important thing, if you look into it, is that the memory hierarchy, when we move from registers, then to cache memory, then to the next level of main memory, and then to disk, the size is always increasing, and size is increasing to a great extent. But the speed is equally decreasing. So the registers are the fastest, then the cache memory, then the main memory, and then the next secondary memory. So here also we discussed about various techniques for improving cache performance. We discussed about various mapping techniques, because if a memory is large, we are bringing some data from a large memory to a small memory, we need to understand that which data we are bringing it where. So the mapping techniques are very much important, and we discussed in detail about all those techniques. And finally, we discussed about the various improvement strategies. So then with week 7.
Okay. In week 7, we started our discussion on arithmetic circuits, because as you know, the computers are supposed to carry out some calculations, and in that sense the arithmetic logic unit can be considered as the brain of the system or the heart of the system. So the actual calculations are carried out there. So in week 7, we started by discussing the various kinds of adders. So their characteristics, their hardware complexities, their speeds, and how we can design them. We discussed the designs of ripple carry adder, carry look ahead adder, carry select adder, and also carry save adders. Then we moved on to the design of signed and unsigned multipliers. We looked at the shift and add kind of multiplication. We looked at Booth's multiplier. Then also we looked at some kind of faster multiplier using combinational blocks, for example, the carry save multiplier, carry save adders. That is a combinational multiplier which runs very fast. And lastly, we looked at the design of various kinds of dividers. Specifically, we discussed 2 algorithms, restoring and non-restoring division, and also we discussed what kind of hardware is required to implement these kind of division algorithms. Then we continued to week 8, where we moved on to the floating point numbers. Well, since we did not discuss floating point number representation earlier, we started by discussing the floating point number format. Now in particular the IEEE standard for representing floating point numbers. Then we talked about how we can carry out floating point addition, subtraction, and multiplication, division, and what kind of hardware requirements are there, what kind of additional processing steps are there. So we talked about those things. Okay. Means our objective later on was to see or explore how these arithmetic circuits can be implemented in an arithmetic pipeline so as to run them faster with a higher latency and lower latency and higher throughput. So we looked at the basic pipelining concepts first. So what are the different kinds of pipelines, how we can schedule the pipeline so that so called collisions do not occur, and then we explored how we can map some of the arithmetic algorithms like floating point addition, floating point multiplication. These 2 examples we worked out into a pipeline. So, one thing we also mentioned that getting a pipeline implementation for division operation, though not impossible, is very difficult. So, the pipeline implementation of dividers requires lot of hardware. So, there are many processors where division is often not pipelined. Then in week 9 we moved on to the input output part of the processing. So, we started with the most important kinds of secondary memory devices that we see or that we use, namely the hard disk, and of course, the competing technology which is called solid state disk, which is very fast replacing hard disks. Nowadays, if you buy laptops, you often come with an option that you can get SSDs or solid state disks instead of hard disks. Because in SSDs there are no moving parts, so while computing, even if you shake your laptop, nothing will happen, which was a danger for hard disk because there was a mechanical moving part. So, if there are any jerks, there was a chance of the hard disk getting damaged. Okay. So, then we moved on to the various input output organizational issues. So, how devices can be connected to the processor, the concept of input output port, the concept of memory mapped IO interfacing, then the concept of IO mapped IO interfacing. So, we worked out a lot of examples to illustrate the basic ideas on these concepts. Then we started our discussion on the various data transfer techniques that are possible. Broadly, we talked about there are two methods, programmed and direct memory access. So, in this week we discussed mostly the programmed IO concepts, mainly the synchronous IO transfer, then the asynchronous IO transfer or handshaking, and thirdly the most important, interrupt driven IO transfer. So, in particular we discussed the interrupt processing in some detail, where we talked about how multiple device interrupts can be handled, how interrupt priorities can be handled, the concept of interrupt nesting, the concept of identifying the interrupting device using the concept of interrupt vector or some other thing, vectored interrupt. So, these are the things we had discussed during this week. Now, in week 10 we first discussed the direct memory access transfer, which is supposed to be very fast. So, instead of the processor executing an instruction to transfer data between an IO device and memory, here there is an external hardware controller called the DMA controller, which takes hold of the memory bus and directly transfers data between IO and memory without CPU intervention. Naturally, all data transfer can be carried out at hardware speed without any instructions being executed. Then we looked at some example interfacing. We looked at the examples of how we can interface a keyboard and a printer, and we discussed how various methods like asynchronous, interrupt driven, these methods can be used along with these kind of devices. For more complex devices, very similar things can be used, but for the sake of illustrations we took two examples which are sufficiently simple and easy to understand. Then we looked at the various bus standards that are existing inside a computer system. So, within a computer system, if you look at an Intel motherboard, there are so many kinds of buses that exist inside the system. These buses are often segregated using some bridges. There is a concept of a north bridge, south bridge, and the various internal buses are connected to one of these bridges. Then you have the external bus standard, which today, well, almost universally we use a standard called USB or Universal Serial Bus. Earlier we had many different standards competing, but nowadays out of a conscious effort by the computer manufacturers, we have zeroed down to a standard, the USB, which can cater to the requirements of various different categories of IO devices, from very slow ones like keyboard and mouse to very fast ones like hard disk. Okay. So, we also discussed this. Now, during week 11, we explored the MIPS32 data path again. So, earlier Dr. Datta discussed the hardware implementation of the MIPS32 instruction set, but here we just extended the discussion and discussed how we can implement MIPS32 instruction execution in a pipeline. Specifically, we talked about a 5-stage pipeline implementation. Because of the simplicity of the instruction set, the pipeline implementation is also seen to be very simple. Then we looked at various different kinds of so called pipeline hazards that limits the maximum speed up that can be achieved in a pipeline. We talked about structural hazards, data hazards, control hazards, what kind of penalties they incur, and we also suggested various techniques by which these penalties can be reduced. Well, in some cases they can be eliminated also. Okay. So, various techniques, various predictive branch performance improvements we had also proposed to improve the performance of a pipeline in general. So, various of these techniques are actually used in modern computer systems today. Though we can call them as advanced topics, but any state of the art processor we see anywhere in our mobile phone, in our laptops, wherever, they use all these techniques in a very big way. And finally, in the last week, we talked about first the multi-cycle operation in MIPS32. So, how we can extend the MIPS32 pipeline to handle operations which may require more than 5 cycles, particularly the EX stage. For the floating point operations, the EX stage itself can require more than 1 cycles to run. Similarly, multiplication division, they may require multiple cycles to run in the EX stage. These are something called multi-cycle operations. So, we specifically discussed how multi-cycle operations can be handled, how data hazards are tackled in such a scenario, how interrupts and exception processing can be done. So, these kind of concepts were discussed here. Then we looked at how we can exploit instruction level processing, instruction level parallelism by using techniques like loop unrolling, which is a compiler technique, so that our target architecture, which today is highly parallel, can exploit the parallelism there. So, given a program, the compiler will try hard to expose more and more parallelism by a concept which is called unrolling the loops, repeating copies of the loops multiple times, so that more parallelism can be exploited. We discussed vector processors. So, how or in what way we can extend the basic MIPS32 pipeline to also incorporate processing of vectors of data. Now, using a single instruction we can operate on 2 vectors, like add V1, V2, V3, 2 vectors V2 and V3 are added, the result will be stored in V1. So, in a single instruction we can do this. So, basically we are avoiding a loop, translating it into a single instruction, that is of course much more efficient. Then we looked at some of the case studies. We looked at in particular the graphics processing unit or GPU, and then we looked at very briefly how Intel processors have evolved over the years. So, this was roughly the total course coverage that we have gone through over the last 12 weeks. Just one point for you. Well, in the examinations that will follow, the kind of questions that you can expect will be quite similar to the assignments that were given to you. So, if you have been serious in solving the assignments, understanding the concepts, so we do not think it will be very difficult for you to tackle the examination. So, let me wish you all the best. So, I request Dr. Datta to also
yes,
say a few
so
words.
as we told in the introductory video that we will be starting with very basics and then we move on with some higher concepts and higher things. So, I think we have done that so far in these 12 weeks, and I must be sure that you have enjoyed this course. At any point of the time you have any difficulties in any section, you can directly contact us through email, and I hope that the examination process that you will be having will be really fruitful and you will be actually gaining something out of it. What said by Professor Sengupta, that you will be getting some question definitely from assignments, that is true, but you should also try to understand and go into the subject such that any kind of question, if it comes, you should be in a position to answer it. Thank you.
Thank you.